Assalamualaikum, my name is Ahmad bin Jalalludin. Today I would like to present my bachelor degree project 2, which entitled Design of Thin Electroplating Jig for Industries. My supervisor is Dr. Muhammad Zaimi bin Zainal Abidin. My panel 1 is Dr. Zulkifli bin Abdullah. Panel 2 is Technologist Dr. Saifuddin Hafiz bin Yahya. And panel 3, Professor Madya Dr. Muhammad bin Minhad. For the problem statement, thin electroplating requires good plating solution flow and good current density coverage from anode to the cathode for uniform coating thickness. However, during commission of a new plating line, the flow and the current density distribution towards to the substrates are unknown and need to be studied. In this study, the thin electroplating buff is withdrawn from original design from Subitek Sanjaya Berhad and computational fluid dynamic simulation is done using various design of a jig in a fixed flow parameter. As you can see in the picture on the left side, the jig acts as cathode which hold the copper 11,000. It is surrounded by titanium basket with thin anode. The objective of this project is to study the jig design for optimum thin electroplating using computational fluid dynamic, which is CFD simulation. And the second one is to correlate thin plating thickness and jig design with CFD result. For methodology of this project, we start from problem statement identification, and then we go to literature review on electroplating, thin plating in industry, cathode orientation, design of electroplating, jig, and plating optimization using CFD. And then we collect data about the current jig design by visiting Subitek company, and then we do the analysis of the jig design. And then we redesign using Solidworks, and then we run CFD analysis. After we have run CFD analysis, we compare the result. If the result is okay, we are going to optimize by using the jig design that is okay. As for result and discussion, I will go through simulation of project, resistance conductivity, flow simulation using improved jig design and original jig design, material selection, and lastly ranking table. Next is simulation of the project. And for this slide, I will show you the comparison of original jig design versus improved jig designs in terms of resistance. For the formula that I will use is resistance is equal to rho times length over A. A is cross-sectional area, rho is electrical resistivity of a material. There are 4 types of material that we compare. The first one is copper, the second one is brass, the third one is stainless steel 304, the fourth one is stainless steel 316. For the resistivity of the material, we get from the internet. For the length and cross-sectional area of the jig, we measured by dividing into 6 sections from the jig body. Each section will include cross-sectional area and its length, and it will be totaled up in the table. After we obtain cross-sectional area and length, the resistance will be calculated using formula, and each material will be summed up their resistance in the table. Now this is the picture of the improved jig design, and the section is dividing into 10 sections. It is slightly different from original because its design has been improved. For its calculation, we also use the same material, which is copper, brass, stainless steel 301 and stainless steel 316, and the cross-sectional area and length will be totaled up in the table, and after that we can calculate the resistance by using formula like we did in the original jig. So the final resistance will be totaled up in each table in each material. The purpose of calculating resistance for the jig is we want to know which material gives the least resistance to the current to flow on the jig. So this is the comparison of the cross-sectional area between two jigs. The original jig have the cross-sectional area of 41.551 meter square, and the improved or new jig have the cross-sectional area of 45.807 meter square. And for the comparison of the length between two jigs, improved jig have score slightly more compared to length of the original jig. For panel information, the new jig design have been made improvement on its bending area, where it can adjustable bend up until 30 degree. After we have done calculation, length, cross-sectional area and resistance for each material, we will know the resistance comparison between two jigs by using different material such as copper, brass, stainless steel 304 and stainless steel 316. From this table, we know that the original jig made from copper has the least resistance, and the improved or new jig will be slightly more from the original jig because they have increased in the length. When we talk about resistance, we take into account the shape of the jig as well. That is its length and the area of cross-section. More the length of the jig, more the resistance. And this should seem obvious considering the charge has to navigate a longer distance to move from one end to the other. Resistance is also determined by the area of cross-section. More the area of cross-section, less the resistance. Next, I will going to explain the flow simulation process. Next, I am going to show you the flow simulation process. For flow simulation parameter comparison, we have three situations to compare between two jigs. First situation is we let the plating tank empty with no jigs and ring. The second situation is we put the jig in the plating tank with the ring. The third situation is we put the jig in the plating tank without cylindrical ring. This is the fluid distribution video which compare original jig and improved jig in terms of fluid velocity. This is the flow distribution table after I have confirmed the key parameter to be measured. We cannot obtain the accurate thickness electrodeposition. However, we can estimate by using Faraday's law electrolysis equation. Next, I will discuss about material selection process. This is material selection table, and the criteria that we compare for our material is the price, density, Young modulus, current conductivity, tensile strength, yield strength, elastic limit, corrosion rate in sulfuric acid. The information about the criteria of the material are obtained from CES EduPack software, medweb.com, and Google. Next is the scoring table. The purpose of scoring table is we want to know the exact value of the criteria that we measure. To do that, just take minimum and maximum value from each criteria and divide it by 2. After we have done scoring table, we will rank the material on the scale 1 to 10 based on their criteria that we obtain from the scoring table. From this table, we know that the stainless steel 316 ranked number 1 because it has the highest total of score with 47 score. And the stainless steel 304 came to second with the 46 score. The third place goes to copper with 41 score. And last goes to brass with 39 score. Refer to the ranking table in the previous show how ranking method will be held. The data collected then will rank from 1 to 10 based on the comparison between the materials. However, since the density and the yield strength of these materials are on par, these properties will be neglected. Based on the ranking table, materials that are first ranked for cheapest are stainless steel 316, followed by stainless steel 304, brass, and copper. As for the conclusion, the first objective, which is to study the jig design for optimum tin electroplating using computational fluid dynamic simulation is achieved. This is because the comparison between two jigs by calculating electric resistance has shown the result that original jig with copper material has the lowest resistance. Hence, the original jig by using copper material has become the favorite choice to optimize the electroplating process. However, when material selection was done and was compared in terms of price, density, Young modulus, current, conductivity, tensile strength, yield strength, and corrosion rate in sulfuric acid, we get to know the best material is not copper, but it is stainless steel 316. This is because stainless steel 316 has excellent corrosion resistance in sulfuric acid. As this project focuses to have the jig design for optimum tin electroplating process, we will neglect other mechanical properties and to focus on two properties, which is electrical conductivity and corrosion rate in sulfuric acid. Thus, it is concluded the most suitable material will be copper material for the jig. The second objective is to correlate tin plating thickness and jig design with CFD result is achieved. This is based on the flow distribution video and its result table in the previous slide. The higher the flow rate of sulfuric acid, the faster the tin plating process occur within Cu 11,000 cylindrical ring, which result into thicker electroplated tin onto the Cu 11,000 cylindrical ring. However, the actual thickness of tin plating must be measured using optical microscope in UTEM. For the recommendation, I will suggest to do further research to compare current tin plating result copper 11,000 with different design of jig. The second one is further CFD analysis have to be done and proposed to the industries to get the optimum result tin plating thickness. The third one is the student must prepare themselves with knowledge of engineering material and material selection.